Welcome guys today. So today we're going to do something very different. uh, we have this is one of the 10 part series on demystifying the Air Academy databank. So we'll start from number one, which a is a famous databank that is usually online. It's very common in Kenya. So we'll look at questions, 10 questions per session. So copyright issues, blah blah blah. So these are the first questions. So you can just pause if you need to write them down, and then go through them one by one. Okay. So just that's number 1 to 3. Okay. And this is number 4 to 4 and 5. Just pause and then write them down if you need to. Then this is number 6 to 8. And then we have 9 to 11. 9 to 11. Okay. The first question. So the first question is on clouds. It's asking what clouds and weather may result from a humid and unstable air mass that is pushed against a chain of mountains by predominant wind and forced to rise. So there are various types of clouds. And they are categorized differently. Yeah. So we have two major types of clouds. We have the stratus clouds. They can be classified in two ways. One is either stratus and cumulus clouds. So in this form, you may have, just from the name, you may have stratus. On this side you have stratus. On this side you have cumulus. And then we have nimbostratus. And then here we have cumulonimbus. Nimbus is the one that is due to the rain. Pardon my chicken, I'm in shells. Cumulonimbus. Okay. So the third one is this is abbreviated as CB. Yeah? CB is CU. It's not necessary here. So we also have altostratus. You have altocumulus. And then we also have another type of altocumulus called altocumulus castellanus. I don't know why that's funny. Okay, so we have altocumulus castellanus, we have cumulonimbus, we have cumulus clouds, and then we have stratocumulus. Yeah, so we can have a combination of these two, which will be part of cumulus, so it will not be strata, so it will be stratocumulus. Okay, good. So that is it about cumulus. And then about stratus, we have stratus clouds, we have stratocumulus, we have nimbostratus, then we have altostratus and altocumulus. Altostratus and cirrus, cirrostratus, and we also do have cirrocumulus, but they are very rare types of clouds. Cirrocumulus. Yeah. Altostratus, cirrostratus. So those are the main two types. The clouds can be categorized in this. This is one of the way that they can be categorized. Where you cuckoo. And then it can also be categorized as low, medium, and high clouds. Yeah. So you have low clouds, medium, and high clouds. This is just to help us in number one. So we want to get the knowledge behind the question. Don't just want to get the question, okay? So the low clouds, obviously, the ones that we experience huku chini, which ones are they? We have the stratus, stratocumulus, cumulus, and cumulonimbus. So we have stratus, stratocumulus, cumulonimbus, and then cumulus clouds. Yeah. Cumulus clouds. Okay. Then also we do have nimbostratus. Good. Then on the medium clouds, you notice they are medium and high clouds are prefixed by something. So medium are prefixed by the term alto. Alto. For the musician, you know that alto is the one that is midway between soprano and tenor. So alto is the katikati, mid, the one in the middle. So we have altostratus, and then we have altocumulus, and then we have the one that we wrote up there, altocumulus castellanus. Yeah. Okay. So on the high clouds, they are prefixed by the word cirro. So this is obviously the first one is cirrus, then cirrostratus, then not cirro as in cirrus, cirrocumulus. Okay, so that's it about a cloud. But this question is asking, what clouds and weather may result from a humid and unstable air mass? So, first of all, we have something called stability. So, the weather can be stable or unstable. Unstable or unstable. Yeah. So a stable atmosphere is that one where, and when air is forced to rise by something, yeah, by a trigger, there's a trigger that causes a parcel of air to rise. So air can't keep on ascending. Why? Because it is most probably colder than the surrounding, so it can't be forced to rise. So that's a stable atmosphere. But in an unstable atmosphere, when a trigger action occurs that causes a parcel of air to move up, it will continue to move up because that parcel of air is warmer than the surrounding. The parcel of air that has been pushed up is warmer, and something that is warm wants to go up. So it wants to keep on rising, it wants to keep on rising. So as it condenses, it forms a cloud that has a vertical extent like that. And this type of cloud is the one that we call the cumulus cloud. It's not there, it's stratus. So whenever you see unstable air mass that is humid, first of all, that you have to know it has to be cumulus. Yeah? Come on, chicken. So it's pushed against a chain of mountains. So for this case, pushed against a chain of mountains. So mountains are very extensive. So a parcel of air is pushed up. So it condenses as it rises, and it forms a cumulonimbus cloud, yeah, of a very great. The nimbus is due to it being humid, yeah. Nimbus is the rain-bearing cloud, and it's usually the dark part that you see. So the answer for question 1 is obviously embedded cumulonimbus cloud. CB is the abbreviation for cumulonimbus clouds with thunderstorms and showers of hail and or rain. Okay, so that's it for number 1. And then let's go and look at number 2. Let's go and look at number 2. Number 2. What does number 2 say? What type of fog emerges if a humid and almost saturated air is forced to rise upslope of hills or shallow mountains by prevailing winds? Okay, so number 2 is asking, what type of fog emerges if a humid and moist saturated air is forced to rise upslope of hills and shallow mountains by prevailing wind? Okay, so we have, for fogs, we have 5 types of fog. We have radiation fog, we have hill fog, we have advection fog, we have steam fog, and we have frontal fog. So just as a summary, the first one, radiation fog, occurs at night when you have at night, because the earth has been taking the heat from the sun. Yeah, it was being heated by day. So because it's a good conductor, it remains to be so. So at night it loses again the heat that it has gained really fast, until such a point that it becomes very cold, and then the air surrounding the earth is cooled. Yeah, so the air that surrounds the layer of the earth like that, this surrounding air that surrounds the ground surface is cooled. So if the air is cooled and you have light winds of roughly 5 to 8 knots, we form this type of fog called radiation fog. Yeah, so there's condensation involved because the air is being cooled to a level that can go to dew point. So if there was no wind, actually we'll only have water droplets. Yeah, so that's why most of the times you wake up and you see your car have some droplets of water. Yeah, so the condition that should be there is clear sky, light wind, and high relative humidity. Clear sky, so that the earth loses its heat so that it can go. So the heat that is lost goes all the way. Because if you have clouds, the heat will be lost and still come back. So you'll have an area that is warm. So there's no condensation that can take place. Then you need light winds of roughly 5 to 8 knots. And these light winds are only found in high pressure areas, remember? Yeah. So we don't have light winds in low pressure systems. Yeah. So this is why radiation fog mostly is at colds, which are moderate. They're neither high pressure systems or low pressure systems, and also they are also found in high pressure systems. Then another condition is that we need to high relative humidity. So the dispersal for most of these is strong winds. Whenever you have strong winds will either clear the fog, or then cause the fog to become a cloud at upper layers. Yeah. So insolation is another way of clearing radiation. Insolation is heat from the sun. As it rises, the air expands and it becomes warmer, and then it becomes even warmer than the dew point. So the thing just clears. We also have hill fog. Hill fog is just when a cloud comes to the covers a high ground. Yeah. So like on a hill, you can find like in Limuru, you can find on those along the road on the escarpment, you can see some of you can see clouds on. So those that the on the hill. So that those are what we call the hill fog. That's the hill fog. And then you have the frontal fog. Frontal fog is usually in front of a warm pressure system. Warm. What no. What did I say? Frontal fog is usually found in front of a warm front. Yeah. So this is roughly where the rain is, because warm front is where warm air is overriding cold air. So these are the clouds, and this is now where rain is, and this is a cold region where it's coming. So this rain is coming from a warm region and it's landing to a region that is cold. This rain condenses at some point, and then it creates something we call the frontal fog. Yeah, frontal fog. Then advection and steam. Advection is just when warm. Obviously, advection. How can you grab it? Warm, something that is warm. You also start with A and then you go to the other letter. So advection is fast, and you don't start with cold. You start with warm thing. So it's warm, moist air overlying, going to a cold surface. A cold can be land, a cold place. So when warm moist air goes to a cold place, it forms what we call an advection fog. And a steam or arctic, called a steam fog or arctic fog, is when a cold air mass goes to a warm moist surface. So it's sort of the opposite of this. So if you know one, you pretty much know the other. So just know advection is the first one. You will start with A, steam fog is the second one. So advection, you always start with warm to cold, and then this one is cold air going to the warm moist surface. So back to our question. Our question was asking which type of fog is, just read from me question 2. Sample, just read it and see what it says. Yeah. What type of fog emerges if a humid and almost saturated air is forced to rise upslope? Yeah. A humid and saturated air is forced to rise upslope. Yeah, that's my chicken. We'll eat it tonight. Upslope of hills or shallow mountains by prevailing wind. So if something is humid and almost saturated, what will it form? When it's triggered to rise, it will form a cloud. And when you have something like a cloud covering a high ground, we have what we call which type of fog? A hill fog. So thank you very much. That is number 2. So let's go to number 3. The relationship between the surface pressure pattern and the pressure pattern in the upper troposphere. What is the relationship? So it's asking what's the relationship between the surface pressure pattern and the pressure patterns in the upper atmosphere. So this one, I'll explain it pretty much simply because I did a lesson on high pressure system. So if you want to know more about it, you can just go back to that video on high pressure systems. So they're asking for the relationship between surface pressure, with pressure at the surface, and pressure at high altitude is the ground. So this is, let's look at the choices. So the first one is saying with cold surface high, pressure passes out. So if you have here on the ground a cold surface high, so we have a high pressure, and this is cold. So definitely, if it's a high pressure and you have a cold obviously will cause then you need to come the isobars to condense. So initially, you had isobars that look like this, ideally. But now, because in this region, if they are cold, it will cause them to condense, to condense, to cause them to bulge inwards. Yeah. So the choice is saying pressure levels bulge upwards. No, they bulge towards the cold. Cold things cause things to come like this. Yeah. So we can't be correct. So then with the warm surface high, so as opposed to this one, this is a cold surface high. So this is a high. So the same types of isobars will be at the same levels as they are here. So imagine how they will be. So high, when something is heated up, it's supposed to expand. Very good. Wunderbar. So they look like that. Not like that. Come on. Very good. Very excellent. Okay, good. Okay. So B saying with warm surface high, low pressure is likely in the upper troposphere. So if you have a high pressure here, so the pressure here, you see the pressure, let me exaggerate it. Let's consider this level, yeah? Okay. So you know that the pressure is high here, maybe here is 100, 1030, 1030, 1030 millibars. So as it goes, it drops, maybe this is 1000, this is 900, this is 800, this is 700, this maybe 750, yeah? So you can look at here on a normal place, here we have 800, but on a high pressure area, the 800 is at a high level, 800 is here. So at high level, you have higher pressure than normal. So if here is 700, the pressure here, this level is not 700. The pressure that is 700 is here. So pressure that is here maybe is 850. So at higher levels, you have tend to have higher pressure. So obviously this one is not true because I say low pressure is likely. So if you have a high pressure here, and this is a warm surface, obviously on top you'll have a higher pressure. Yeah, because if you have a warm column of air, obviously on top you have so the warmth is the one that determines. And same to here, if you have a cold column of air, on top you'll have lower pressure than normal. Yeah. So you always compare it with the normal. You don't compare it with anything else. So see, it's a with a cold surface high, low pressure is likely in the upper troposphere. This is what you have said. That here you have a lower pressure than 700. You expect to have 700 here, but 700 is already here, and the higher you go, the lower the pressure gets. So here could be less than 700. So that's your answer. Okay, so let's go to number 3. What situation is called overdevelopment on a weather report? So overdevelopment is just when clouds are forming, many clouds are forming going vertically upwards. So it's just vertical development of cumulus clouds to rain showers. Okay, so it's just that. Yeah, there's no two here about it. So the next one is number 5. Is asking what is the composition of air? What is the gas composition of air? So for this one, you need to know the actual there is a scientific one that is very up to spec, very specific, So, but as we know that nitrogen, and the good thing with this, you just know something like nitrogen and oxygen. Just by looking at the choices, you know which one is. And so this one we take it to be at 78%. Oxygen is 21% approximately. So oxygen 21, nitrogen 78. So there's only one answer that gives you that, and that is the answer. So the other because 78 plus 21 is 99. So the 1% is water vapor and other gases. Water vapor and other gases. But you can go to specifics of maybe carbon dioxide, because I know oxygen is not 20, it's 20 point something. Yeah. So your answer is B, because that's the only answer that gives you nitrogen and oxygen of 21%. So with these things, you don't even if you don't know things to the specific level, you still have a very good chance of passing. So weather phenomena, number 6, weather phenomena are most common to be found in which atmospheric layer? So we have 4 atmospheric layers. 4 atmospheric layers. So the lowest one, the one near the surface, is called the troposphere. Troposphere. And then there's a boundary between then we have the stratosphere. Middle between these two, we have what you call this boundary, the boundary between the two is called the tropopause. Tropopause. On top of this, we have so aviation will mostly interested in this. But anyway, you need to know everything, because you live in this world. Who do you expect to know this world for you? Yeah? Go with this, we have the mesosphere. Then here we have the mesopause. And then we have the ionosphere. Okay. Or at times they call it the thermosphere. So troposphere, tropopause, stratosphere, stratopause, mesosphere, mesopause. Okay, that's it. So they're asking us. So most of the weather phenomena occurs until the troposphere. Why is this the case? Because in an ideal situation, the height of this troposphere, the height of the tropopause, which is the boundary, the marketing, the topmost part of the troposphere, it is determined by temperature characteristics. Because here on the tropopause, the higher you go, the cooler it becomes. The higher you go, the cooler it becomes, until you reach this tropopause, where the temperature remains constant. So the higher you go, the temperature remains constant. The higher you go, the temperature remains constant. And then you reach a point where now, the higher you go, the temperature increases. Yeah, gradually, and then all the way up to the stratosphere. So most weather phenomena, because on the troposphere, what can I say? So let's talk about the troposphere. On the Earth, the height of the troposphere at the equator ranges from 10 to 18 kilometers. So it's usually, the height is usually, 16 to 18 at the equator. Then here at the pole, it ranges from 6 to 8 kilometers. And then at mid latitudes, it is about 11 kilometers, the height of the tropical poles. So you can see that at the equator, the distance is very big as compared to the pole. Where the Nini is this layer that we are calling the troposphere. So if you have a very big distance here, and you know the higher you go, the cooler it becomes. So here you're going very far, very big distance, farther and farther away, higher and higher and higher and higher and higher, the higher you go. So the temperature here at the equator is very cold. It's colder than the temperature at the pole. So just to mention. But most of many are found, weather patterns are found in the troposphere. Yeah, most of the patterns are found in the troposphere. So, and in ISA, they take the height of the troposphere to be a general height of 11 kilometers. Yeah, that is what we use in International Standard Atmosphere. So, for those of you who are not doing aviation, we have what we call International Standard Atmosphere, but that now is the ideal atmosphere where planes are meant to fly, and it's given by the body of the UN that deals with aviation, which is called the International Civil Aviation Organization, which is initialized as ICAO. Okay, so that's the troposphere. So what the weather phenomena most common to be found in the atmospheric pressure, atmospheric layer, is the troposphere. Number 7 is asking what is the mass of a cube of air with edges of 1 meter long? So a cube, something like looks like this. A cube, it's like a box that has equal length, width, and height. So it's sort of like that. So it's 1 meter, 1 meter, 1 meter. So you remember from high school that the volume of our body is given by 1 times 1 times 1, length times width times height, which is 1 times 1 times 1 meter, which will give you 1 cubic meter. And then this guy is asking, what is the mass? What is the mass of a cube of air that has those dimensions in accordance to ISA? So we know that in ISA, the density of air is given as 1.225 kilograms per cubic meter. Yeah, that's the ISA density. So here they've given you the mass is 1 meter. So you ask yourself, if 1 meter in ISA they're saying a cubic meter by volume of air weighs 1.225 kilograms. Here you're given a cube of 1 meter which has a volume of 1 cubic meter. So what is the mass? They're asking for the mass because we know the density is equals to mass over volume. So we have the density, which is 1.225, which is equals to mass times the volume is 1. So our mass is 1.225 kilograms. As simple as that, which is so. Before we go, I just want to mention the International Standard Atmosphere calibration. So we have what we call the International Standard Atmosphere. So instead of, this is an atmosphere that runs all the way from the ground to the space, yeah. So if you're given an ideal situation, so they will have to define for us every part of the atmosphere. That the atmosphere at this point, the temperature is this, at this point, the temperature is this, or the pressure is that, at this level, at Nairobi, the temperature is this, at New York, the temperature should be that, because the planes are everywhere at every time. But they don't need to do that. For you to give an ideal situation, you just need to define the base, and then anyone can extrapolate from. If you want maybe at a height of 10,000, you just extrapolate from the base all the way. So what ISA have done, they have just given mean sea level values. So the mean sea level values are given us. So the temperature on the ground at mean sea level is 15 degrees Celsius. The density, you have seen, the density is given by as 1.225 kilogram per cubic meter. Then you have what we call the lapse rate. Lapse rate is the rate at which temperature changes with height. So the lapse rate is given as 1.98 degrees Celsius per 1,000 feet. So there's a drop. For every 1,000 feet you go up, there's a drop of 1.98 degrees, almost 2 degrees. 1,000 feet, 2 degrees. Remember, at the ground it's 15. So at 1,000 feet above mean sea level, the temperature should be 13. Yeah, temperature should be 13.02. Okay. And then what have I forgot? Temperature, density, and pressure. Pressure is given as 1013.25 millibars or hectopascals, or in inches it can be given by 29.92 inches of mercury. Okay, so that's just that. So unless there's any other thing you need for me to mention, just put it in the comment section. I'll address it. So the next question, at what rate does the temperature change with increasing height according to ISA ICAO standards? So according to this, how does the temperature change in height within the troposphere? Okay, now I've remembered. So the temperature changes at 1.98 per 1,000 feet, which is 2 degrees per 1,000 feet. You have, obviously the temperature decreases by 2 degrees per 1,000 feet. So here's your answer. So let me mention something on that. The goodness of doing questions. Let me just wrap this for now. So ask yourself, so this lapse rate, it doesn't go, it is from the ground, the temperature drops at 1.98 degrees per 1,000 feet from the ground to 11 kilometers, which is approximately 36,090 feet, above which the temperature remains constant. Above which temperature remains constant at minus 50, minus 56.5. Should not wrong. Just confirm for me. Minus 56.5 degrees Celsius. Okay. Yeah. So let's go to the next question. What is the mean height of the tropopause according to ISA? So I told you the height of the tropopause in ISA is 11 kilometers, which is equivalent to 11,000 meters, which is equal to 36,090 feet. And then most cases you will not be given the temperature maybe in degrees per feet. You'll be given in degrees maybe per meter or degrees per any other thing. Okay. So what you do, if you want to convert 1,000 feet to meter, you know that 1 meter is equals to 3.28 feet. So what about 1,000? So you'll get a value that is approximately 300. So whenever you have 1,000, so you can just say 1.98 degrees Celsius per 300 meters. Yeah. So if you want it in 100 meter, divide by 3, get 100, and also we divide this by 3. Then I think 0.65 degrees Celsius per 100 meter. And you see, even in those things that we discuss, dry and wet lapse rate, environmental lapse rate, just use this. Whenever you have 1,000 feet, just put 300 meters and then cancel, you get the answer. You don't need to cram all of this, just need to know one and then you know how to convert from one form to another. So the term tropopause is defined as, obviously the tropopause, we said it's the boundary layer between the troposphere and the stratosphere, as simple as that. Then temperature will be given in by meteorological aviation services in Europe, are in which unit? So temperature is given in degrees Celsius or degrees centigrade, the same units. Yeah? So temperature can also be given in other units such as Kelvin. So you have Celsius, you have Kelvin, and we have Fahrenheit. So I think you have had a question before asking you to convert Celsius scale to Fahrenheit or Kelvin to Fahrenheit or Celsius to Kelvin. And then you ask yourself, what was that formula again? You don't need to remember any formula. Yeah? So you just need to know there is water boiling point and water freezing point. Boiling point and freezing point. Okay. So in the Celsius scale, who has said Celsius? Oh my gosh. In the Celsius scale, temperature boils at 100 degrees Celsius and freezes at 0 degrees Celsius. In the Kelvin scale, just need to know the freezing and boiling point. In the Kelvin scale, water boils at 373 and freezes at 273. Then the Fahrenheit scale, the temperature, the freezing point is 32 degrees Celsius and 1 and 2, 12 degrees Celsius. So you see 32, sorry, this is Fahrenheit. So I want to ask a question that you reply to me in the comment section. What is 32 degrees Fahrenheit plus 32 degrees Fahrenheit? Write your answer in the comment section. So to 12 degrees Fahrenheit, 32 degrees Fahrenheit. So what happens is this, for Celsius to Kelvin, just look at this difference. The difference between 100 and 0 is 100. This one between 373 and this one is 100. Wow, I never seen that. Just saw it now. What's the difference between 12 and 32? It's 108. So the difference is so the only thing that's funny is this bugger called Fahrenheit. These guys in the US, yeah, the guys who always want to be different. So who are we? Who are we? Just, just the rest of the world. Okay. So this is it. So back to conversion. So let's say you want to convert from Celsius to Kelvin. So it's just linear. So if I need to convert 50 degrees Celsius to Kelvin, I just add it to 273 plus 50. Why? Because 50 is here and my starting point was 0 to 50. But here my starting point is not 0, so it can't be 50 Kelvin. My starting point is 273, so I need to add I don't need to add. I need to add 50 from 273, which comes to E of 323 degrees Kelvin. Okay. So, and if I want to convert 200 degrees Kelvin to Celsius, to degrees Celsius, what do I do? I minus 273. Yeah, so I don't add. Now I minus 273. So 200 minus 273, get minus 73 degrees Celsius. Good. And then the last one is Fahrenheit to, from Celsius to Fahrenheit. So from Kelvin to Fahrenheit, don't need to do that. You can just convert it to this and then that, because this is direct, so just know one. So if I need to convert 60 degrees Celsius to Fahrenheit. So first of all, I'll consider this ratio is 100, this is 180. So the ratio is 100 on the Celsius scale is equivalent to 180 on the Fahrenheit scale. The difference, yeah? So what about 60? 60 is from 0 to 60, somewhere there. So 60 is the one that we want to convert. So how is 60 degrees Celsius? So 60 will be 60 over 100 by 180. So what do you get? 108 degrees Fahrenheit. But this is not the answer, because 60 was starting from the freezing point of water, 60 going up. Then you have converted using the scale and you found it from here going here up to here on the Fahrenheit scale is 108. So you need to add 108 from the freezing point, which is 32. So it's 108 plus 32. You get 140 degrees Fahrenheit. And then to convert from Fahrenheit to the other way. So for example, if I want to convert 90 degrees Fahrenheit to Celsius, so I need to know from 32 it goes to 90. So what's this value? What's this difference? So I need to know how this gap is how much. It's not 90 because you're not starting at 0, starting at 32. So you need to do 90 minus 32 first. Then you get 58 degrees Fahrenheit. So from here to where 90 is, it is 58 degrees Fahrenheit. So, and you know the ratio is 180 degrees equivalence. It corresponds to 100 degrees Celsius. What about 58 degrees? 58 over 180 by 100. So it's approximately just use a calculator. You can just use a calculator answer. So your answer will be in degrees Celsius. Okay, so that's all about that, and we are done. So as our confirmation, you can just look at the conversion. For conversion, you can go to your Google, then type Celsius to Fahrenheit. So for example, the first one was 60, and we got our answers 40. Good. And then the next one was Fahrenheit was 90. So our answer here should be 32. In case of any question, just write it in the comment section. Let's meet for the next 15 questions. Hope you enjoyed. Thank you. Feel free to subscribe, and you can also send your donations to the number on the screen. Cheers.